a body of mass 15 kilograms falls under gravity. Okay, so we can see the direction clearly it's going in. Alright, it's going down. We've got A there to represent the direction it's falling in. So it experiences a resistant force of 3V. Okay, and it says then find the time it's taken for its speed to increase from 29 to 39. Okay, so in this case then, of course, we've got the force pulling it down due to gravity. Okay, so the force then, mass times acceleration, so it'll be the mass, which is 15, times the acceleration due to gravity, which is g. So applying then Newton's second law, okay, in the direction of increasing motion, well, we've got the resultant force then equals to mass times acceleration. So the leading force, the driving force, is the force due to gravity, which is 15g. Take away the resistant force, which is 3v, and that equals to then mass, which is 15, times a then the actual acceleration of the object, okay, following the resultant force of the gravity affecting it and resistance holding it back a little bit. So in this case here, okay, what I might be tempted to do, okay, just like we've done previously, is divide through by 3, okay, and the reason for that is because I can make that to be 1 here. So that's something you can sort of think about in future when it comes to these sort of setups. You could divide through by 3 there, that becomes 5, that becomes 1v, and that becomes 5a. It's just going to make the integration slightly easier to deal with, okay? Don't forget then that g is 9.8, yeah? So you get 49 minus v is 5a. And then, of course, we know a is dvdt. So we've got 49, take away v is 5 dvdt. Separate the variables. So we get the v's on one side, take the dt up there. So the integral of dt equals to, and leave the 5 where it is, but write it outside of the integral because it's a constant, multiplying it, and then 1 over 49 minus v dv. Okay. Right, so then when you integrate this, then we're going to have t here. And when you look at this here, well, there's linear on the bottom, so it'll just be ln we're going to use, okay, straightforward. One other thing though to note, which would actually make life a little bit easier, instead of doing a constant of integration, what you could do is appreciate that we want to find the time taken here for its speed to increase from 29 to 39. Okay, so what we can do is apply limits to this integral from 29 to 39. Okay, and if we do it that way, we then don't have to bother with trying to work out the constant of integration. Okay, it'll all work out the same, but this just saves a little bit of time, right? So we could do it this way instead. This is just an alternative way. You could have done the previous ones like this as well. Okay, so it's just something to think about here in regards to this. It's going to get the same answer out, just a slightly different approach. So when you integrate this here, you get t. Okay, now remember here, differentiate the bottom, you get minus 1. We haven't got minus 1 up there, it's just 1, so I can make it a minus. So I'm effectively timesing it by minus 1, but then you've got to compensate them by dividing by minus 1. Okay, all right. So it all works out nicely. So you end up getting minus 5 here, ln then of that bottom, and then you put the limits in between 39 and 29. Okay, you don't have to use limits, as I said. You could put plus c, and then you could go through the process. You could say, look, when t is 0, v is 29, and you could work out what c is, and then it'll figure its way out then from there. But this is just a slightly quicker approach here. So if you put the limits in, t will be equal to minus 5 ln 49 minus 39. So you put the upper limit in first, take away then, put the lower limit in, you got minus 5 ln 49 minus 29. Okay, so if you do all of that, t turns out to be minus 5 ln, that becomes 10, and then minus minus becomes a plus 5 ln, and that becomes 20. Okay, and you end up getting 3.466 seconds when you calculate that on your calculator.